Thank you for joining us. Our research covers machine learning and asset management. I'm Satyan with Flexstone Partners.
Hi everyone, I am fourth year PhD student in Industrial Engineering and Operations Research Department at Columbia University. I am currently working with Professor Ali Hirsa on machine learning applications in finance, mostly in asset management.
So we will begin by giving you an outline of how our presentation will flow. As you'll see, the idea is to set a framework and to highlight the key research aspects that Columbia and we are focused on. And that spans from liquid products to illiquid products. And then we will conclude with what we have found and some of the extensions of the applications. As you see, mostly machine learning applications in asset management are already here. So what we are doing is accretive to the research there. Our focus has been to combine the research that is getting done, as well as making sure that it can be utilized from a practical perspective. So the way we like to think about approaching the research and the topics is in terms of three pillars. Most people try to focus on the analytical tools. Obviously, when you hear of Columbia, you're also thinking like that. But for us, for the problem to be solved, we have to focus on all three components. The first component is the data component, and this is key. And we'll get into the details around these components in the following slides. But for us, the data has to be cleaned, processed, and utilized in the right way. The right analytical tools have to be built, and the visualization has to happen so that the end user or the research scientist is actually having something that is usable. From a data perspective, there are many issues that we have to deal with. First one is just accessing the data set. We're obviously at the Bloomberg conference, which is a large data provider. There are others. There's Reuters, there's Morningstar, there's GDelf, there's FactSet. And you can imagine that merging all these data sets together and making them useful is quite a challenging task. There are a lot of subcategories and categories that have been cleaned up. The different providers that I mentioned also deal with the data in slightly different ways. The way they roll the dates, the way the valuations are done, the way the information is processed, the way the APIs work, and so on. The last challenge also is that for financial assets, you're dealing with managing non-stationary data. That itself is a challenge for some of us that have dealt with this. So for us, a large part of the effort is making sure that we are using the right data, and that requires product knowledge, sector knowledge, and industry knowledge to be able to process it. The second pillar that we have, that I laid out in the beginning, are the analytical tools. This allows us to go beyond what most of the other participants do that are not utilizing machine learning. So the key concept you have to ask yourself is, what is the management application that we are trying to solve for? Whether it's the signals, the sentiment, the scraping, the clustering, what particular topic is that particular tool using the data to solve for? So as the data comes in, we are trying to predict what's going to happen in the future. And as new data is coming in, you're supplementing that information and trying to reduce the tracking error. It could be that we are trying to predict how the price of the volume is going to do, or how a particular mutual fund manager is going to perform, or it could be whether how the fund is going to go up or down in value. Lastly, as you see in the last bullet, there are thousands of key questions that could be addressed. But of the thousands of key questions, you also have to ask yourself, which is the real key question for that particular topic. And finally, you're talking about the visual part, and this is the third pillar, and it's equally important because your computer screen, your real estate is expensive. So for us to give you graphs and charts, there are many report writers and many solutions. The point here is, how do we demonstrate and show the results in an effective way so there's minimum time wasted and the information is meaningful to the user? Another way to look at this is the basic framework that we put together, where you see the data coming in, getting processed, the machine learning algorithms working, and the final predictions and calculations and classification models running to give some sort of a visualization on that problem set. So that laid out the basic framework and the three pillars as we approach every problem. So we, with Columbia, have worked on, like I said, the liquid components as well as the illiquid products. And within that, the framework, What we're going to show today is some of the work that we have done for mutual funds that can be extended to private equity funds, real estate funds, and so on. And for that, Tugce will join.
Hi, so I will continue from mutual funds framework. In the first phase, we deal with the manager selection problem. And here we have alternative data and holdings data. What is alternative data? Alternative data is the information about a company that is published by sources outside of a company. It could be fund style, it could be manager information, it could be sustainability, firm level data. Everything can be included in alternative data. So what is the holdings data? Holdings data is the data related to the holdings of a fund. It could be turnover ratio, expense ratio, management fee, and we have so many features on this site. And we will use LSTM algorithm as the optimization method, but I will go into detail in the following slides. In the second phase, we deal with the portfolio construction asset allocation problem. When it comes to asset allocation, there are so many different methods. Like there are traditional methods, there are optimization algorithms, there are deep learning, clustering, reinforcement learning algorithms, and we will come into detail in the following slides. And the third phase is the stress testing real-time impacts phase. And the fourth phase is the visualization. And once we have all these models, as Satya mentioned, the visualization is one of the most important things. We need to show it because we can't show our performance by using the visualization. And the fifth part is the market indicators. And in this part, I will talk about macroeconomic indicators, jump prediction, and sentiment data. So our first phase of the problem is the manager selection problem. Our motivation here is that which managers may outperform given objective functions. By saying objective functions here, I mean the performance measures. It could be Sharpe ratio, it could be max drawdown, it could be Kalmar ratio. According to the appetite of the modeler, we decide on which objective function we will use in our model. And Satya mentioned the data part is one of the most difficult parts in our model. And as I mentioned in earlier phase, we do have the alternative data, we do have the holdings data, and we have this data for 10 years for more than 25,000 US mutual funds. And this number of features are more than 1,000. So the first phase here is the processing part. How do we process this data? We can build new features based on the data we do have in this alternative data and holdings data. And we have so many features, so not everything could be useful in our model. So we need to implement feature selection algorithms to decide on which features are important given the objective function. And once we decide on our features, our data, the next phase is the deal with this data. Like we may need to do dimension reduction, and we may need to deal with the categorical data by hot encoding them. And once we decide on that, as you can see, the second phase is the clustering part. We are implementing k-means clustering algorithm or other clustering algorithms as well in order to come up with new features. And once we have these features, we are implementing a long short-term memory method, LSTM, for only time series data. And in convolutional neural networks, we also incorporate these cluster-based features into our model as well. And based on our benchmark, Sharpe ratio, Kalmar ratio, or max drawdown, it could be, and we build our model and we build our prediction framework. And once we have our model, by using this performance prediction of the performance, then we rank our funds from 1 to 5 according to their performance in the objective function. And the last phase is the visualization phase. Once we implement all our models, we also come up with a visualization of how to show our performance better. Here we did it for only Sharpe ratio, but we do have this for all other benchmarks as well. Okay, the second phase of our model is the asset allocation portfolio construction part. And here our motivation is that in the first phase, we decide on which funds we will have in our portfolio. But after we have our funds in our portfolio, now we also need to decide on how to allocate our resources on these funds. Like, again, the objective functions are the same. Like it could be Sharpe ratio, it could be Kalmar ratio. According to how we want to model it, we decide on our objective function and try to allocate our resources. And the first phase is the traditional methods. Like there are so many traditional methods. In traditional methods, we take the historical return data, we implement our traditional method, and based on the performance of this current phase, we try to decide on the performance of the next phase. But it doesn't make so much sense, right? Because we are using the current data, current performance to predict the performance of the next phase. Therefore, what we thought about is that we still use the return data. We use traditional methods to estimate the current period asset allocation strategy. And by going back in time, by using the LSTM model, we take into account the trend more, and then we decide on how should be our allocation strategy for next period. So in terms of the traditional models, one of the most important ones here is, as we know that Harry Markowitz's model, it is a mean variance optimization model. In this model, our purpose is to maximize expected return of a portfolio given a level of risk. And what we want to do is that create as diversified as possible a portfolio and try to obtain maximum return by minimizing our risk. I will not go into detail of this model, but continue with the other traditional models. And the first one is the equal weight allocation model. This is the simplest way to allocate our resources. This is non-informative model. We just give the same weight for all the funds in our portfolio and then go with this strategy. And the second one is Sharpe ratio-based allocation. Here, Sharpe ratio measures the performance of an asset compared to risk-free asset and adjusted for its risk. In this phase, we exclude the ones with the negative Sharpe ratio because it means that the performance of the fund is even worse than the risk-free asset. Therefore, there is no meaning to include it in our portfolio. And we continue with positive funds and then normalize our Sharpe ratio and take them as our weight. The third one is a Kalmar ratio-based allocation. Kalmar ratio uses max drawdown to measure the risk and combines it with profit and loss. Here, the max drawdown means the maximum observed loss from a peak to a trough of a portfolio. Here, we again exclude the ones with the negative value because it means net loss for us and implement the algorithm as the same way we did in the Sharpe ratio. And the last one is a mixed ratio-based allocation. Here, we combine the Sharpe ratio and Kalmar ratio. And again, we exclude the one with the negative value because it means net loss again. Once I talk about the traditional methods, then how we implement the machine learning in asset allocation. So here is an example. Like we use a nested clustered optimization algorithm for allocation, better allocations. This paper is by Marcos Lopez de Prado. In this method, we first do take the input as our return and covariance matrix. Once we have them, we denoise this matrix. We reduce the covariance matrix by denoising. And then by doing detoning, we remove the market component from the denoise correlation matrix. Once we have our correlation matrix, what we have to do is that we do clustering based on this correlation matrix. And but we use here the k-means algorithm and come up with the clusters of our funds. And once we have the clusters, in the fourth phase, we optimize our cluster allocations by using convex optimization methods. And here we decide on the allocations within the cluster for each of the clusters. But what we need to do is right now to allocate our resources between the clusters. And in this phase, we apply some shrinkage procedure to shrink our covariance matrix. And once we have this new matrix, what we again implement the same methodology, convex optimization, to come up with the allocations for between cluster allocations. And the last allocation will be the multiplication of the between clusters and within clusters allocations. And we also implement reinforcement learning in asset allocation. As I mentioned before, we use LSTM based on our performance measure and come up with the weights of the portfolios according to our objective function. But we don't know which one is actually working best in the environment. So we want to come up with a combination of these models and try to predict the overall weight of the model. And here is the beta IT is the combination weights, and WIT is the predicted portfolio weights from each LSTM model. Here our purpose is to try to find overall weights. But unfortunately, as you can see, there's an epsilon. And for epsilon, we need real data, but we don't have the real data. Therefore, we need to use a technology to estimate the epsilon. And here we use Holt-Winters method. And by using Holt-Winters method, we estimate epsilon. Therefore, we estimate the final overall weights. Once we implement all these algorithms, we want to see which one is actually working better. So visualization is very important in this phase. For example, in the top left first two plots, you can see that we plot the different performance of the different methods. And you can see the top one, the purple one, is the Sharpe-based ratio model, Sharpe ratio-based model. And it performs better. So it allows us to see which one is actually working better in current time framework. And also, we incorporated the reinforcement learning into these models as well. And in the bottom plot, you can see that the reinforcement learning algorithm is actually doing a very good job compared to all the traditional models. And we are currently working on more models on this phase. These are our preliminary results, but it will continue to come in the later phase. Okay, now we decide on the allocation manager selection. We pick our funds. And in the second phase, we decide on how to allocate our resources between these funds. And the third thing is to test the market conditions and portfolios against the historic scenarios and need to assess impacts. Here we can do stress testing in order to see the resilience of the models under possible crises like 2008 economic crisis and our current crisis, which is COVID-19, for example. In this phase, what we do is that we take our current allocations and go back into time and to these scenarios and try to see if we are under this same scenario again, how will be our performance in this case? And also, we also try to see the real-time impacts. In this phase, we are using NLP and sentiment analysis to see how it will be affecting the sectors, portfolios, and others. And the last phase here is the market indicators phase. In here, our motivation is identify the relative potential and attractiveness of sectors, subsectors, other given the market and economic conditions. Here our data consists 8 sectors. There are different sectors, but currently we are using 8 sectors: consumer goods, energy, industrials, utilities, technology, materials, financial services, and healthcare. Here, what we do is that first classify our sectors, subsectors, and then compile macro and cohort-specific data, and train our models for common macroeconomic and sector-based indicators over various time horizons. This is our framework. At the first phase, we need to do data collection, and we are doing lots of literature review on which features should be better for which sector. Like some sectors could be, some data could be useful for healthcare sector, but some data may not be useful for other sectors. And therefore, we are working with macroeconomic indicators data and performance benchmark data by sectors. In the feature engineering part, we determine the most important features for each sector. Here, some of the factors are common for all of the sectors, like, for example, GDP, unemployment rate. These are the common macroeconomic indicators we can use for all the sectors, but also there are other sector-specific indicators we come up for each sector separately. And once we have all our data, we implement machine learning and deep learning algorithms to predict the performance benchmark data for each sector. Once we predict the performance, what we do is that only the ranking the sector based on this predicted value. Here, I want to specifically talk about this example, this application of the machine learning in market indicators example. Here, what we want to do is that we want to predict for very long horizon to see the performance in the long term. But once we run our traditional recurrent neural networks models here, we encountered with the vanishing gradient problems. Once we did some literature review, we come up with echo state networks by Herbert Jaeger. And we are currently using this in our model. And here, this model is the reservoir with fixed weights solves the vanishing gradient problem in traditional recurrent neural networks. And the output is a linear combination from the reservoir. Therefore, a linear regression algorithm can be used to predict the output weights, which will be very simple compared to the traditional recurrent neural networks. And it works faster than traditional recurrent neural networks. The reason is that we don't have any backpropagation algorithm here. The algorithm is very simple. Therefore, it is very, very fast, and we don't encounter any vanishing gradient problem. And here I want to talk a little bit about how it works. We have 3 layers, one input layer, one internal layer, which is reservoir, and one output layer. And we have three weight matrices from input to reservoir, within the reservoir, and from reservoir to output. And at the beginning of the algorithm, we generate these weight matrices randomly, but we don't touch the weight matrix from input to reservoir and within the reservoir during the training algorithm. We only train the output weight matrix. You can see the equations below. The algorithm basically has two phases. In the first phase, we update the reservoir states. And in the second phase, after we calculate all these states, then we only train the last phase, last weight matrix by using mostly we can use the linear regression algorithms, and we can come up with the output weight matrix. And here the f is the activation function, but f out is usually the linear activation function. Therefore, we can implement linear regression. As I mentioned earlier in the framework phase, we are also considering jump prediction. And by using jump prediction, our purpose is to show that how the unexpected conditions in the real life can affect our models and can affect our ranking. Here, we filter our data based on different filtering algorithms and then try to predict the signal on this filtered data. And we also want to see how the effect of news will be on the ranking. And here we also use different algorithms like BERT model and IDF model. And again, the visualization is the most important part. In the left side, you can see the results of the ecosystem network in our model. And you can see that the healthcare sector and the industry sector and utility sector, they are well fitting on the model. And for the right side, you can see the results of the jump prediction. We did the 3-year trend simulation and 5-year trend simulation for utilities sector. And you can see our plots here. And these are our preliminary results, and we are currently working on improving our models better. Now I am handing over to Satyan.
Thank you, Tugce. I think what we have laid out right now is the framework, as you saw, in combination with the data, the analytical tools, and the visualization. And we've tried to give examples of how the applications are, where data is more freely available. For example, for mutual funds, we all know, Tugce mentioned 25,000 mutual funds. Data comes from Bloomberg, data comes from Morningstar, and so on. Now, the next challenge we have is applying the same framework to a more illiquid product. And I'm not going to get into the definition of the illiquid product, but let's think it from a data perspective, where the data is also not widely available and so on. So in private equity, if you look at the framework, it's very similar to what Tugce was walking through in the prior slides. The manager selection equivalent on private equity would be the company selection or the GP selection. Which GP do you want to invest with? So like we selected the managers based on the data portrait that we put together, putting it through the analytical models and try to predict the performance, the process here is quite similar. There's a universe of managers, there are a universe of GPs. We calculate, we combine, and we process the data on each GP, on each investment team member, on each officer, and so on. And we try to predict the performance of that particular GP's underlying portfolio. Similarly, on investment selection, the criterion here is the same, depending on which industry or sector or deal or co-investment is attractive. The process is the same. And in the end result is building a portfolio, just the asset allocation part that Tugce was talking about previously. The market indicator parts for private equity are quite similar also. We were predicting out which particular sector or subsector is going to outperform, and we can bring this into the investment selection. So if you like consumer products, we should be able to isolate the types of consumer products given the current environment. Or if we think that healthcare sector is going to outperform for the next 4 to 5 to 6 years, then it should be given an overweighting in the manager selection if you're constructing a fund portfolio, or in the underlying investment selection if you are a GP who's trying to construct a portfolio. So I think the applications that we are finding, or the utilities we are finding from the work we are doing, actually stretch from the illiquid assets to the liquid assets and vice versa, because the work itself, the framework, it's turning out to be quite fungible. Once we have the pillars in place and the models that we think can jointly process the data and predict and do a good job, we are seeing that applicability is uniform. The only thing that is different, obviously, other than the features and the number of variables and so on that you have to train the models on, those will be different. But other than that, the data that you have to provide is also different. I mean, here for private equity, for example, you have unique data providers, and similarly for real estate, you have many data providers. The challenge here is to making sure the data between them is uniform and we can process this, and they allow us to do that is also the question. So what we're going to focus on here is essentially just one component which is slightly different than the liquid part, which is the cash flow forecasting and cash flow modeling. And if you can imagine, this gets into the valuation piece, the stress testing piece, and so on. So I will hand it back to you, Tugce.
I will continue with cash flow forecasting in illiquid products. There are two parties in private equity, general partner and limited partner. Limited partner puts the money into the investment, and general partner is the one who is doing investment with the fund's committed capital and manages this investment and also seek the exit opportunities for this investment with sizable returns. And at the beginning of the agreement, the limited partner and general partner agree on some money, the limited partner will be liable during the life of the fund. This is called the commitment. And you can see in the figure that at in the first years of the fund, usually there are negative cash flows. The reason is that the general partner is making investments during the first couple of years. It is mostly the first 4 years of the fund. And whenever there will be an investment, the general partner will ask limited partner for contribution. And the later phases of the fund, there will be more positive cash flows. The reason is that some of the investments will exit with returns, and there will be returns, which is called distributions for limited partners. And as you can see, there is a general shape, which is J curve here, but we don't know when will be the contributions and distributions will be, and what will be the size. We don't know when general partner will make investments and how much will be these investments and when will be these investments. And we don't know when there will be an exit in the investment and what will be the size of the returns here. Therefore, we have a couple of questions. We wonder what are the contributions and distribution profiles? What impact do unplanned events have on the profit? Like, we don't know, for example, COVID-19, how it will affect the contributions and distributions. And we wonder how close is the profile to the generic sectors or subsectors profiles. Like, can we use this model for all the sectors, or do we need to build different models for different sectors? And once we have these questions, we also have some challenges in the data. The data is sparse and difficult to access. And there are different data sources we can have, but they are mostly not publicly available. Even if they are publicly available, we cannot reach this data very easily. Like, we can only download a couple of rows per day, which is not very useful for us. And the data is not standard. For example, the vintage year can be the year of the first year of the investments in the fund, and it could be also the first contributions made for the investment purposes, like the first year of the investment contributions. Therefore, there is no standardization here. We need to be very careful while processing the data. And unfortunately, the updates are not doing very frequently. Therefore, we also need to be careful on this side. We can see that this problem is pretty complicated, but we have some traditional methods dealing with this problem. The first problem is, the first paper is by Takahashi and Alexander. This is also known as Yale's endowment model. This model is discrete time and deterministic, and there are certain assumptions and input parameters to be estimated. Like, for example, we need to estimate the growth rate, we need to estimate the ball, or we need to make assumptions on them. And also, contributions and distributions are dependent to each other in the formulations. And once we have the wrong forecasting for one of them, we need to start building the model from the beginning. Therefore, it is difficult to update to the recent data. And in order to overcome these problems, there is one stochastic modeling paper from the Bachner and others. This model is continuous time and stochastic, and there are two independent stochastic processes for contributions and distributions. And it is good that, because if there's anything wrong with one of the forecasting, we can only do this stochastic process, but not the other one. But still, there are certain assumptions here. Like, the distributions assumed to be follow log normal distribution, and the contributions assumed to be follow the mean reverting square root process. Therefore, still there are assumptions. And what we want, we don't want assumptions. Therefore, we want to build assumption-free models. In this purpose, we want to use machine learning algorithms. Here, our key challenge is the data is not consistent and data is not sufficient. Therefore, we need to implement interpolation algorithms to increase the frequency of the data. We are using Brownian bridge, and also we are using variance gamma bridge. The reason we are using variance gamma bridge incorporates the jumps in the market. Therefore, it will fit the realistic scenarios. And also, we have different fund types, like buyout, real estate, venture capital. And for each of these funds, we have different characteristics. Therefore, we need to build models separately for them. And again, as in the stochastic paper, we predicted contributions and distributions independently. And as you can see, we have the data from 2014 to 2019. And for quarterly benchmark data, we have buyout, real estate, and venture capital fund types. And since this is most likely time series data, we are implementing LSTM, long short-term memory method. We are implementing various types of the LSTM, like encoder, decoder LSTM, CNN LSTM, convolutional LSTM, and bidirectional LSTM. Once we have the model, we again have the visualization. Here, I want to show one of our applications, machine learning applications for cash flow forecasting. Here you can see that we pick the buyout funds here. We have the contribution and distribution data, and we predict net asset values by using this formulation below. And then we pre-process this data to make sure that this data size is equal for each data. And then we train our model with LSTM and bidirectional LSTM models to predict our net asset values. We try to predict as long as possible to have the long-term predictions. And once we have the model, we test our model with actual fund data, actual fund net asset values. Here you can see that the first two plots here belongs to the CNN LSTM model. It is made for the contributions, and the interpolation technique used is Brownian bridge. And you can see that the training set is fitting very well to the predictions. But for testing set, we have over prediction. But you can still see that the trend is the same. We only need to calibrate our model better. And in the right plot, you can see that according to the framework in one slide before, we predicted the net asset values from our machine learning implementation and compare them with our actual net asset values. This is a preliminary result we have for cash flow forecasting, but we are currently working on different models. And now I am passing to Satya.
Thank you, Tugce. So as you see in conclusion, and hopefully you got a little taste of the types of research projects that we're working on, the extensions of these projects, once we have built the framework, once we have tested out exactly what kind of models are being applied to the financial markets in a good way, and which are the ones that have value, the extensions that we're working on is the applicability to ETFs, the applicability choosing hedge funds within the manager pool, real estate portfolios, particular sectors or locations within real estate that could be meaningful. So the extensions and the projects we're working on are quite large, and obviously it's a huge space to explore, and we're quite excited about that. One of the things we do want to mention is that all of the research that is being done here from the students and the professors and the PhD students at Columbia is available for everybody. And we thank you all for joining us.